Today, I want to tell you about high-performance liquid chromatography, or HPLC. This is a powerful tool that scientists use to separate, identify, and measure different parts of a mixture. It's important in many fields like medicine, environmental science, and food safety. HPLC was developed in the 1960s from an older method called liquid chromatography, which used low-pressure glass columns. Scientists improved it by using high-pressure metal columns, allowing them to push liquids through much faster and more efficiently. HPLC is incredibly useful. In the pharmaceutical industry, it ensures that medicines are pure and have the correct amount of active ingredients. Environmental scientists use it to find pollutants in water and soil. In the food industry, it checks for additives and ensures products are safe to eat. To better understand high-performance liquid chromatography, HPLC, let's take a look at a schematic representation of an HPLC system. Here are the key components. Solvent, this is the liquid that carries the sample through the system. It is also known as the mobile phase. The choice of solvent depends on the type of mixture being analyzed. Gradient valve, this valve controls the mixing of different solvents. It allows for the creation of a gradient, where the composition of the solvent can change during the run. This helps in separating components with different properties more effectively. High-pressure pump, this pump pushes the solvent and sample through the system at very high pressures, up to 400 atmospheres. This high pressure is what makes HPLC much faster and more efficient than traditional liquid chromatography. Sample injection loop, this is where the sample mixture is introduced into the system. The loop ensures that a precise volume of the sample is injected into the flowing stream of solvent. Analytical column, the heart of the HPLC system, this column is packed with a stationary phase material. As the sample passes through, its components interact differently with the stationary phase, leading to their separation. Detector, after separation, the components exit the column and pass through a detector. This device identifies and measures each component based on their unique characteristics. Common detectors include UV-vis spectroscopy and mass spectrometry. Computer, the computer collects and analyzes the data from the detector. It processes this information to provide a clear output of the separated components, often in the form of a chromatogram, which shows the different peaks representing each component. Diving deeper, HPLC manifests in various forms tailored to different analytical needs. Normal phase, employing polar stationary phase material, and nonpolar mobile phase, ideal for water-sensitive compounds and isomeric separations. Reverse phase, utilizing nonpolar stationary phase material and a polar mobile phase, offering versatility in separating polar, nonpolar, ionizable, and ionic compounds. Ion exchange, equipped with ion-containing stationary phase material and a buffer-based mobile phase, facilitating the separation of anions and cations. Size exclusion, leveraging porous stationary phase material, molecules diffuse into pores and are separated based on size differences. Now, let's dissect the intricate machinery that powers HPLC. Pump, positioned at the forefront, the pump generates high-pressure flow of eluent from the solvent reservoir into the system, crucial for solvent delivery. Injector, nestled next to the pump, the injector introduces the sample into the solvent stream, either via a syringe or an autosampler system. Column, the heart of the system, where separation unfolds within its stainless steel housing, packed with silica or polymer gel material, replacing traditional glass columns. Detector, working in tandem with the column, The detector observes the separation process, detecting changes in eluent composition caused by the presence of analytes, translating them into electronic signals. Recorder, capturing these electronic signals, the recorder transforms them into visible data, facilitating analysis and interpretation. Degasser, ensuring the purity of eluents, the degasser employs polymer membrane tubing to remove gases, preventing the formation of air bubbles that could disrupt the separation process. Column heater, vital for temperature-sensitive analysis, the column heater maintains consistent temperature conditions, enhancing reproducibility and resolution. Safety considerations. Chemical hazards. Be aware of the various chemical hazards involved in the experiment, especially with flammable organic liquids used as the mobile phase and potentially toxic or biohazardous samples. Chemical exposure. Always wear personal protective equipment, prepare solutions in a fume hood for ventilation, and ensure solvent reservoirs and waste containers are tightly sealed to prevent exposure to hazardous vapors. High pressure. Monitor pressure levels to prevent accidents, and wear appropriate eye protection to mitigate the risk of eye injuries from leaks. Fire. Take precautions to prevent fires by ensuring proper maintenance of the system and avoiding ignition sources near flammable chemicals. Mechanical or electrical problems. Regularly inspect and service the HPLC system to prevent mechanical or electrical issues that could compromise safety. Ventilation controls. Ideally, locate HPLC waste vessels in a fume hood and ensure the system operates in a well-ventilated negative pressure room. Documentation and training. Complete all necessary training and review safety data sheets and manufacturer manuals before using the HPLC. Personal protective equipment (PPE). Eye protection. Wear ANSI Z871 compliant safety glasses or safety goggles. Protective clothing. Use a lab coat and appropriate chemical-resistant gloves, ensuring suitable clothing is worn underneath. Preventive maintenance. Regularly clean and maintain equipment to ensure safe operation. Use high-quality solvents and filters, degas the mobile phase, and inject clean or filtered samples to prolong the life of injector and column. Flush rinse the instrument regularly to prevent residue buildup and change seals and O-rings according to the manufacturer's schedule. General safety measures. Avoid sudden changes in pressure and temperature, and choose a suitable mobile phase to avoid damage to the stationary phase. Avoid injecting complex samples directly into HPLC columns, rinse the column frequently, and store it properly to maintain performance. Install the column correctly to prevent leaks, prepare the mobile phase meticulously, and equilibrate the column before use for consistent results. By adhering to these safety precautions and operational guidelines, users can ensure the optimal performance and longevity of their HPLC system while maintaining a safe working environment.
This is all about today's topic. Thanks for watching Funny EHS Info. And don't forget to subscribe our channel to get immediate notification of our videos. Share our videos to your friends and colleagues to create safety awareness. If you have any questions and requirements, please comment in comment box.